of one dimensional. And what do we mean by inviscid? Inviscid means the fluid should not have any viscosity. That means this is basically applicable to ideal fluids, because all real fluids have viscosity. So the moment you say that it is applicable to inviscid flow, that means it is applicable to ideal fluids. And finally incompressible. Incompressible, as we have seen, means that the density does not vary along the fluid flow direction. So under these assumptions you can apply Bernoulli's equation to any 2 points on a streamline. And the Bernoulli's equation is also applicable to any 2 points of the flow field when the flow is irrotational in addition to one dimensional, inviscid, steady and incompressible. What it means is, if the flow is irrotational in addition to steady, incompressible and inviscid, then you can also apply Bernoulli equation to any 2 points in the flow field, it not necessarily on the same streamline. What do we mean by irrotational flow? Irrotational flow means the fluid particles do not undergo net rotation. So that is what is known as an irrotational flow. Now the Bernoulli equation is given by this expression. You can write it in different forms. For example, if you write it in the form of head, that means in the form of pressure head, velocity head, static head and total head, you get this kind of an expression. Here this term, as you can see, is known as pressure head, and this term is known as velocity head, and this term is known as static head. And here P is the static pressure, rho is the density and g is the acceleration due to gravity, and v is the velocity of the fluid, and z is the elevation with reference to a datum. So basically what the Bernoulli equation written in terms of the head says that the pressure head plus velocity head plus static head between any 2 points in the flow field or between any 2 points on a streamline is constant. That means the total head is constant. You can also write this equation in terms of pressures. That means you can write this in terms of pressures as static pressure P, velocity pressure rho v square by 2 and pressure due to datum. So Bernoulli equation when written for in terms of pressure states that the static pressure plus velocity pressure plus pressure due to datum, called as total pressure, remains constant under the assumption stated earlier. Now between any 2 points in the flow field you can write Bernoulli equation in this form. For example, I am writing this between point 1 and 2, then the summation of static head plus velocity head plus head due to datum is equal to the static head plus velocity head plus datum head at point 2. And as I was mentioning, for real fluids the flow is not inviscid, that means viscous effects are there in real fluid. So you can modify Bernoulli's equation and by including what is known as a head loss term. So this is known as modified Bernoulli equation. That means it is nothing but Bernoulli equation with provision for viscosity by including head loss term. So in this expression all these terms are known to you. One additional term is HL, which is called as head loss. So now let me show the pressure variation. Let us apply the Bernoulli equation to a pipe flow and let us see how the pressures are varying. Let us say what we have here is a uniform cross section pipe through which a fluid is flowing, okay, and we would like to plot different pressures. Now let us to start with, let us assume that the flow is inviscid, that means the fluid does not have any viscosity. Since the cross section area is same here, that means area at any point is same. So if you apply continuity equation, at any point v is constant. So velocity does not change along the length. Since velocity pressure is equal to rho v square by 2 and rho is constant here, the velocity pressure also will remain constant because v is constant. So if you are plotting pressure, different pressures versus length, you find that for the velocity pressure you get a horizontal line. Okay, so this is a line for velocity pressure. And if the fluid is ideal, then the static pressure also remains same. So this is the static pressure line for the ideal fluid. Since the total pressure is summation of velocity pressure plus static pressure, the total pressure line is also horizontal. So total pressure at any point is equal to velocity pressure plus static pressure, and it remains constant throughout the length. So this is the application of Bernoulli's law to an ideal fluid. Now what is the effect if viscosity is non-zero? That means if the fluid is viscid, or it has finite viscosity. For viscous flow, the velocity pressure still remains same, because from the continuity equation velocity at any point should remain same. Okay, so this horizontal line applies to both inviscid as well as viscous flows. So velocity pressure remains horizontal only. Then what happens to the static pressure? Static pressure continuously reduces in the direction of flow because of the viscous effects. That means there is a loss of static head due to viscosity. So you see the a sloped dashed line for viscous flow. Okay. So the total pressure is nothing but the summation of static pressure plus velocity pressure. So and the velocity pressure is remaining constant and static pressure is reducing. So the total pressure also reduces in a real flow, and this difference between the total pressure at the inlet minus total pressure at the outlet is nothing but your head loss. So this is the application of Bernoulli's equation to a pipe flow. Now let us say that we would like to maintain the same pressure at the inlet and as well as the outlet, and the flow is inviscid. That means we want to maintain P1 should be same as P2, and similarly static pressure at the inlet should be same as static pressure at the outlet, but the fluid is viscid, that means it has viscosity. Then how do we ensure this? So whenever you have viscous flows, and if you want to have same pressures at the inlet or outlet, or if the inlet pressures are greater than the outlet pressures, then what we have to do is we have to use some kind of a pump or a fan. For example, if I am using a pump here or a fan here, okay, then it is possible to maintain the same static pressures and the total pressure at the inlet and outlet. What happens when you have when you are putting a pump? When you are keeping a pump or a fan in the pipe flow, the velocity pressure does not change, because the fan or pump does not increase the mass flow rate, so velocity pressure remains same, but it increases the static pressure because it adds energy to the fluid. So at the point where you have added the pump, the static pressure increases. Okay. Since the static pressure increases, the velocity pressure also increases. So you have the modified pressure lines with the addition of pump or fan inside the fluid circuit. Now that is what is shown in this slide. This is a modified Bernoulli equation with friction and a fan or pump, and I have shown here an arbitrary cross section. That means cross section area need not be constant, and the fluid enters here and fluid leaves here, and this is the fan or a pump. So what is the modified Bernoulli equation for this kind of a situation? This is the modified Bernoulli equation, only the difference is this. So this is nothing but the head gain due to the presence of the fan. If P1 is equal to P1 by rho z is equal to P2 by rho z, and V1 square by 2g is equal to V2 square by 2z, and Z1 is equal to Z2, then these terms get cancelled out, and you have Hp is equal to H loss. That means the head gain due to the fan should be sufficient to overcome the head loss due to friction. Now what is the power required to drive the fan or pump under the case discussed just now? So this equation gives what is the power requirement when you are using a fan or a pump. This again is derived by using Bernoulli's equation, and what we have here, this m dot is nothing but the mass flow rate of the fluid, and this is the head loss, and this is the static pressure at the outlet, static pressure at the inlet. V2 square minus V1 square is the difference divided by 2 is the difference in velocity pressures at the outlet and inlet, and this is the difference in the datum heads. And here eta fan is the efficiency of the fan. That means if the fan has some inefficiency, then you have to take that into account. So this expression gives you the fan power required or pump power required. So you can by applying Bernoulli's equation, you can find out what should be the motor capacity to drive the fan or pump. Now let us apply this Bernoulli equation to a very simple case. So this is an application of Bernoulli equation to a venturi. Now what is a venturi? Venturi is a device for measuring flow rate. So, basically normally it is used for measuring air flow rate or water flow rate. So, as you can see in the figure, it consists of a straight portion, then a converging portion and a gradually diverging portion. So, this is your diverging portion, this is the converging, and where the diverging and converging portions meet, you call it that portion as the throat of the venturi. And here this is the inlet to the converging portion is 0.1 and the throat portion is 0.2. And the venturi has a manometer here, and one end of the manometer is connected to the inlet to the converging section, that means 0.1, and the other end of the manometer is connected to the throat portion, that means 0.2, and this manometer is filled with some manometric liquid. So, basically the air flows through the manometer, and because of the air flow there will be some pressure difference in the manometer, that means there will be a manometric head here, and from the characteristics of the venturi and from the by measuring the manometric head you can calculate the air flow by applying Bernoulli's equation. So, now let us look at the problem statement. It is given here that the areas, cross sectional areas A1 and A2 are 0.5 meter square and 0.4 meter square. That means area at this point 1 is 0.5 meter square and area at point 2 is 0.4 meter square, and the density of air is 1.12 kg per meter cube, and manometric fluid used here is water, and it has a density of 1000 kg per meter cube, and the measurements show that the manometric head is 20 mm, and it is also given that acceleration due to gravity is 9.81 meter per second square, and we can neglect all frictional effects. That means we will be applying the original Bernoulli equation, because we are assuming the fluid to be incompressible, steady, irrotational and inviscid. So, frictional effects need not be considered. So, if you apply Bernoulli equation, let us see what happens. First, what is the required output? We have to find out what is the mass flow rate for this venturi, which shows a manometric head of 20 mm. So, the equations for mass flow rate is rho AV, mass flow rate at any point, is equal to rho into cross sectional area at that point and velocity at that point. So, you can write this expression for mass flow rate, and from continuity equation nothing but conservation of mass equation, A1 V1 is equal to A2 V2, because we are assuming the fluid to be incompressible. So, rho A at any point is constant. So, from this equation you get that A1 V1 is equal to A2 V2, or velocity at the point 2, that means velocity at the throat can be expressed in terms of the areas, cross section areas at the throat and at the inlet to the converging section, and the velocity at the inlet to the converging section. So, V2 is equal to A1 by A2 into V1. Now, let us apply Bernoulli equation. If you are applying the Bernoulli equation, you can slightly write it in a different form. Datum head is change in datum head is 0. So, we can write the Bernoulli equation in this form: P1 minus P2 is equal to rho A into V2 square minus V1 square by 2, and P1 minus P2 is nothing but the pressure difference between the point 1 and 2, which can be obtained from the manometer reading as rho g h, where rho w here is the density of the water, g is the acceleration due to gravity, and h is the manometric head. So, if you use the input data and these 4 equations, you will find that the mass flow rate of air is equal to 11.18 kg per second. So, this is one very useful application of Bernoulli equation to a venturi meter. There are many other applications of Bernoulli equation. As I mentioned, it is one of the most useful equations, and you find its applications particularly in air conditioning or duct design and in refrigerant piping design, etc. We will be using this equation repeatedly, but you must keep certain things in mind. Even though Bernoulli equation is very useful, you must be aware of the assumptions under which the Bernoulli equation is valid. For example, Bernoulli equation is not valid when you have a duct where there is a sudden expansion. When there is a sudden expansion, what happens is the fluid gets separated. That means there will be separation of fluid, and the flow no longer remains one dimensional. So, you cannot apply Bernoulli equation, because you remember that Bernoulli equation is a scalar equation and it is applicable to one dimensional flows. So, whenever you have 2 dimensional, 3 dimensional effects, you cannot apply Bernoulli equation. Number 1. And second thing is, if you have a fluid flow where there is a lot of heat transfer as the fluid flows through the duct, then also you cannot apply Bernoulli equation. Then because what happens when there is a large amount of heat transfer, then the density may not remain constant as the fluid is flowing through the conduit. That means the assumption of incompressible flow will not be valid. So you cannot again apply the simple Bernoulli equation that we have discussed here. So when you are applying Bernoulli equation, first make sure that the assumptions or the conditions are met, and then apply the Bernoulli equation. Of course, Bernoulli equations are also been developed for unsteady flows and also for compressible flows, but we will not be discussing those issues, and these will be discussed in applied fluid mechanics courses. Right. Now let us look at the evaluation of pressure loss during fluid flow. We have seen that generally in one of the most common problems or common requirements in the design of an air conditioning duct or in the design of a refrigerant piping or in a chilled water piping is to find the capacity of the motor or capacity of the pump. What should be the power consumption, or what is the power consumption of the pump, so that you can select a suitable motor for the pump or the fan. So you have seen from the modified Bernoulli equation in the presence of viscous effects and a fan that the pump power depends upon the mass flow rate, and it depends upon the inlet and outlet pressures, velocities and datum heads, and the friction losses, that means the head loss. So if you want to find out what is the power requirement, you must know what is the head loss. Okay, and normally in any given problem, the mass flow rates is an input, and the pressures and velocities are also inputs. So if you know the head loss, then you can find out the power input. So a key problem here is to find out what is the pressure drop as the fluid flows through a conduit. Now the loss in pressure is due to fluid friction and turbulence, change in fluid flow cross sectional area, and abrupt change in fluid flow direction. That means the fluid undergoes pressure loss due to these three effects: friction and turbulence, change in fluid flow cross sectional area, and abrupt change in fluid flow direction. A pressure loss due to friction and turbulence is known as frictional pressure drop, and pressure drop due to change in cross sectional area and abrupt change in fluid flow direction is known as minor loss. That means frictional losses, all losses due to friction and turbulence are known as frictional pressure drops, and losses due to change in cross sectional area and change in direction are known as minor losses. Sometimes the name minor losses could be a misnomer, because in some situations the minor losses can be much more than the frictional pressure drops. So you have to keep it in mind, and you should not neglect the minor losses thinking that they are minor. Now the frictional pressure drop. The frictional pressure drop is given by Darcy-Weisbach equation for internal flows, and it is given as delta Pf is equal to F L by D into rho V square by 2. This is the frictional pressure drop, and here L is the length of the pipe or tube or the duct, and D is the internal diameter if it is a circular pipe or tube, or as an equivalent hydraulic diameter if the cross section is non-circular, and rho, as you know, is the density and V is the velocity. So if you know the density, velocity, length, diameter, and this factor, then you can find out the frictional pressure drops. Now what is this factor F? Factor F is known as Darcy friction factor. It is a non-dimensional factor, and it depends upon Reynolds number and relative roughness of the internal surface. Now what is Reynolds number? I am sure that again you studied about Reynolds number in your course on fluid mechanics, but let me just give it for the sake of completion. Reynolds number is a dimensionless number that quantitatively relates the viscous and inertial forces, and whose value determines the transition from laminar to turbulent flow.